All right, folks, let's dive into some weld design. This is going to be kind of broad introduction, and then down the road we can get into more details, probably in another class. All right, a little history on welding. You probably get more information from the Google. Different types of welding methods. Let's just go through kind of quickly um, different types. So submerged metal arc basically means there's some kind of a flux, there's metal, there's an arc between the base metal, there's some kind of welding machine which connects to the electrode and to a ground, so the current flows one of these directions, and then there's some kind of a joint prep. So when we look at um, another type, submerged arc welding, we would have some kind of flux, a bare electrode, an arc, and when this arc happens, it melts the flux, which creates a molten flux and protects the molten metal from oxygen. If it touches oxygen, the metal reacts and corrodes, and that's what causes spattering in welds, is that reaction of the molten metal with the atmosphere. Gas metal arc, so in this case there's a gas, so there'd be kind of a nozzle with gas around it, and then an arc in the base metal. So in this case, the gas creates the protective shield. Gas metal arc is great in the shop. In the field, it gets difficult because it doesn't take a ton of wind to remove that oxygen or remove that gas shielding. All right, flux core is another type where there's flux inside of the welding wire, and that burns. As it burns, the metal gets deposited, the burning flux creates gas, and you get protection of the weld. That's very common outside um, because you don't have to have gas bottles, but again, it's subject to the same problem with weather, particularly wind. Electroslag is another method which you tend to see in shops. So anyway, as you're beginning a project, it's important to understand the weldability of the steel. If we're using common structural materials like A36 or A992, it really doesn't take any thought because those are weldable. We know they're weldable. They're made to be weldable. Sometimes when we get into older steels like this head frame here, this is down at a mine in New Mexico. We were doing some repairs to that, and one of the first things we did was take a little test coupon out of an area that wasn't highly stressed, sent it to the lab, and received what's called a carbon equivalent, which tells you, um, based on the different alloying elements, how weldable the steel is. So if we can use this type of table to understand the weldability of the material. All right, different welding codes. D11 is the primary structural code. 1.4 gives guidance on welding reinforcing steel, and D1.8 is seismic. There's also a bridge welding code. American Welding Society is what AISC defaults to for the very nuanced specifics of welding. Um, there's also weld quality requirements in D11, D18, D14, and different types of inspections. All right, it's important to understand the different ways welding can not be great. So briefly, no fusion, where the weld really didn't get hot enough. This is usually caused by poor welding technique and poor settings on the machine. Gas bubbles, they tend to not be the biggest deal because they're rounder than, say, cracks, but we don't want them in there. Cracking obviously carries no load. An undercut where there just isn't enough weld metal deposited. slag inclusions, and then in this case, lack of penetration, where to fix this, you come back and gouge out or grind out this backside and then fill it back up. All right, inspection. There's 7 requirements for any inspection program. So if this happens to be a direction your life takes you, um, you need to tell someone what to look for, when, how, where, how often, what the threshold of detection is, and probability of detection. Non-destructive testing finds problems without destroying the material, which is extremely valuable. This here is a magnetic particle test. So this little device here in this fellow's left hand creates a magnetic field. This sprays iron filings, very fine filings, and if there's any cracks or discontinuities, hold on a second. If there's any cracks or discontinuities, those iron filings coalesce around the crack and basically show you the crack. Other types of testing, liquid penetrant, it's surface cracking. You put a liquid on the part, wipe it off, and then with a black light, you can see if there's any penetrant left over, which is seeped into cracks. So these first two, well, actually an eddy current find cracks near the surface. And then if you want to go deeper, you can use ultrasonic or radiographic. So this is an ultrasonic test here, where the inspector is looking inside of the part. Let's see if there's a machine and a screen connected to this, so it's kind of like looking at an ultrasound of a baby. It's hard to really tell what's going on unless you've been trained. All right, threshold of detection here is given, and it's important to understand this, that you can't find cracks under a certain size, and you can't find cracks over a certain size, but if you look at these 1/4 inch maximum size, those are very visible, so it tends to be realistic to find them. Although if you're looking inside, anything over a 1/4 inch, you're not going to be able to see with ultrasonic. Okay, residual stresses as the weld shrinks at different rates, or the base metal is cool and the weld metal is molten. As the weld shrinks, it creates residual stresses. There's a British standard 7910, which will give you the ability to calculate those. API, which is American Petroleum Institute, allows you to relax those stresses. British standard 7910 does not. Constraint. So basically, this is kind of key here. Constraint produces triaxial state of stress. So tension stress in 3 directions. This reduces the ability for plastic flow. Plastic flow occurs due to shear stress. Less plastic flow means less toughness. So if we look at this curve of fracture toughness of thickness versus K1C, so fracture toughness, these dips tend to be like foils. The normal thicknesses we work in are kind of in this range. So you can see as you go from thinner material, say 1/8 inch, 1/4 inch material to 1-2 inch material, you get a decrease in toughness. This K1C is a plane strain fracture toughness, and that's kind of the minimum of fracture toughness for thicker materials. So if we base our designs for civil structures generally off of K1C, we're going to be in a good range of understanding of fracture behavior of our structures. All right, so little bit on joint types. There's different ways the joints are configured. Butt joints are common in splices. T-joints are common when things come together. Lap joints have their place. Here's some more joint layout examples. So this would be a angle welding to a gusset plate, and the example that I've given you is actually that. Some people like to put more weld on the leg side and less weld on the other. Generally, the fill just wants to weld, so I don't think it's a problem to have them balanced. Um, Here's a joint in a truss. Lots of different ways to do it. The key to this is thinking about the people building it and configuring the joints in a way that's helpful to them. We can calc things pretty easily, but as we design joints and welds and bolted connections or whatever, thinking about how does this get machined, how does it get welded together, how does it get bolted together in the field or whatever, really makes for better connections if we're thinking with the builders in mind. All right, let's look at some different groove weld types. So a butt weld would be where you put two pieces of material together, just burn it in as much as you can, and you get some amount of penetration. Partial pen weld would be where we've beveled an edge and filled it up. Double bevel here, this would be a complete joint pen weld. Same with this. This single bevel is pretty common. You'll notice that in these parts only one side is beveled. There's no reason to require the fabricator to bevel two parts. It just increases their labor costs. And then fillet welds and flare bevel welds. This should say flare right here, where the radius is curved. Okay, so let's go ahead and move on. Different welding positions. The flat position is ideal because the weld metal, when it's molten, just flows down into the joint. Horizontal and vertical are the next preferred and can be somewhat challenging. Overhead can be quite challenging because molten metal tends to drop out of welds overhead. In this case, there are special electrodes that we can use that are more friendly to overhead welding. But as we consider the joints we're designing, it's important to consider what we're asking people either in the shop or the field to do. Okay, weld symbols. So this gives you kind of an idea of everything that goes into a symbol. It can be fairly complicated. Um, but let's just take it step by step. So this arrow points to this. This is the near side of the joint. This is the far side of the joint. So the near side info is on the bottom. The far side info is on the top. If we want the same weld on both sides, we don't need to fill out the far side. Some engineers will fill out both. To me, that's just duplicating information if it's identical. Now, if you want something different on the opposite side, then sure, by all means, fill this out. However, if we have, in this case, a fillet weld on both sides, which is what this symbol means, and it's a 1/4 inch, all I have to do is put that here and life's good. All right, so A is the weld size. It's always to the left. If this were on the other side, this symbol wouldn't flip. You'll notice here, this fillet has the vertical on the left, and on the other side, or actually, that doesn't really, yeah, that does. So this would be the left side, so the arrow would be here, and this would be the right side, the arrow would be here. You'll notice the symbol orientation stays the same between these. You don't mirror them. Anyway, so weld size on the left, weld length or pattern. So maybe you have a 10-inch weld, you put that here, or maybe you want 6 inches every 12 inches, you would put 6-12 right here. Far side info, we talked about that. The weld symbol, what type of weld. And if you come down here, you can see the different weld symbols for the different types of welds. D, weld all around. So sometimes like on a column base plate, we'll weld all around the column. Field weld, we want to indicate welds we think are going to be done in the field. It's kind of a hint to the contractor that, hey, this is a field weld, this is going to take some coordination. It doesn't have to be done in the field, and there may be shop welds that we specify that the erector and fabricator come to terms on about welding in the field. Um, I like to put a note in my general notes that says it's up to the general contractor to coordinate with the field erector and the fabricator what is field welded and what is shop welded, and I don't want to take responsibility for that. So I make sure they understand it's their problem. And then the weld leader, and then on the left with this little caret are any notes. So if we come down here, we can see the different symbols. We kind of talked about that. And then more info from the code. So here, so I have on the left the joint as drawn. So this would be what's shown in the drawing. In practice, that's what this means. So 1/4 inch double-sided fillet weld done in the field. Here's in metric a 5 mm flare bevel weld where I want 20 millimeters of weld for every 50 inches. So that's what this looks like. And then if I looked at the side view of this, the weld would start and stop. Here's a 1/4 inch butt weld all around. So I'm saying this would be like, say, 2 pieces of pipe coming together. That butt weld would go around it. Here I'm saying a complete joint pen, 45-degree joint prep, which generally I don't like to do, but a detailer would call this out. And then it's double-sided beveled. So that's what this is. Generally with CJP welds or PJP welds, I like to leave it up to the contractor or the fabricator to decide what their joint prep is like, because that will relate to their shop practice, and I like to leave that up to them. All right, here's a partial joint pen in metric where it has a flare bevel prep. The G stands for grinding it flush afterwards. The 10 is the joint depth, and the 8 in parentheses is how much actual weld metal or penetration there needs to be. It gets more complex than that. I like to keep the engineering call out simple and then allow the detailer to expand on these symbols based on shop practice and agreements or discussions they've had with the fabricator. All right, let me start another video since I'm only about halfway done here.